Proof of Concept podcast, the tech show where we explore real life use cases from the field and discuss some of the hot questions in the field of data science and AI. I am your host, Grant Case, and today we have a very special guest with us, Simon O'Toole. And today we're coming back into our whole let's talk about industry, but in this case, we're not talking about industries and AI. We're talking about astronomy, man. We're going out into space and it's going to be awesome. So, Simon, please introduce yourself to the audience.
Hi, so I'm Dr. Simon O'Toole. I was once a research astronomer, which means that I used to actually study the stars, and my goal was to study the stars and look for planets around stars other than the sun, and I did find a few. But then about 10 years ago, I made a transition over from research through to sort of IT and data, and now I mainly focus on data engineering, and we're moving into the future, as we're going to talk about today. I think into more data science side of things, and this is a big thing. Astronomy has always been a really good area for data science back before it was called data science, because we always had relatively large volumes of data, and that's only going to get larger and larger as we go into the next decades. So I'm really excited to talk to you guys and to talk to Grant. So yeah, I think this is a really exciting topic, and hopefully we can inspire some people to get out there and start looking up.
Yeah, awesome. Awesome. And so what we like to do when we talk about here on the Proof of Concept podcast, we like to kick it off with cool stuff with this technology. And Simon, and kind of our pre discussions, you guys are doing some really cool stuff with this technology. Can you kind of talk a little bit about first, maybe how you're kind of sourcing the data, and then kind of what you're starting to do with all of this data? There's so much good stuff happening around astronomy right now. We've got the James Webb Telescope. We've got new stuff coming on down the pike. So tell us a little bit about what's cool in astronomy right now.
Yeah. Okay. So I mean, basically, what we're doing here. So we're at Macquarie University, and we take data from a whole lot of different telescopes. Often it's been processed already, but not always. And so this is one of our biggest challenges, is to get data from telescopes. So telescopes are in remote locations. They have to be either very dark, away from city lights, and away from bad weather. So particularly rain and cloud and
Mhm.
everything like that. But also, that, I mean, that's the case where you have mirrors and lenses and stuff that you'd be probably familiar with. But in the case of radio telescopes, so like the dish out at parks, you need to be out away from radio interference. So that could be microwaves, that could be mobile phones, anything like that. So you have to get away, and you also don't want it to be windy, because if you've seen that movie, The Dish, you will remember that they had big
Mm.
winds, and you have the giant dish that acts
Yeah,
like
you have the
a
big
sail.
sail out there. Just whoop,
Exactly,
there it goes.
and they weigh hundreds of tons, and that would not be a good result if that came crashing down. So they need to try and get those facilities as remote as possible, and that's awesome, because you get these high quality signals, very faint things in the distant universe. But the problem is that you've then got to get the data from those remote locations to somewhere where you can process it, because you can't put a supercomputer or some kind of high performance system out in the middle of nowhere. You don't have the facilities or the amenities. You have enough
Amazon isn't
computing
putting
power
in a new
to run it.
region out there.
No, that's right. You don't. You will not get. You will not get to. Not get too far from, or too close to an Amazon center. That's for sure.
Yeah.
So yeah. So that's the big challenge that we have now, is just moving the data around. We have large volumes. So when you have a raw data coming off these telescopes, optical telescopes, things tend to be a little bit more contained. You're probably talking about, in one observation, you might have about 128 megabytes worth of data, although some of the next generation telescopes coming online next year, the Vera Rubin Observatory, for example, will be acquiring around about 30 terabytes per night. We'll come to
Ooh.
that, I guess, in a moment. But then you get down to the radio telescopes, and they'll have the square kilometer array, which is really the next generation facility that will come online in around about a decade or so. There's a lot of technical challenges to work out first, but that's where we're talking about anywhere from around 9 terabits per second. So that's about 1 terabyte per second,
Wow.
Um, and I've even heard numbers. It does depend a little bit on who you speak to, but I was at a meeting just last week, and they were talking more around the closer to a petabit per second at the full
At the full
the full sort of
strength,
data rate, full strength. Yeah.
it
And
do
at the moment, we don't have the technology to deal with that. I have also been to some talks recently where they've said, oh, well, they can build a big enough pipe, like fiber optic cables and that kind of stuff, and combine it. And they're doing testing now where they can get around that 1 petabit per second, but only around 10 kilometers at the moment, and only in sort of really trial
please hook
conditions and
that
all of
up to
that
my
sort of stuff.
house, please.
But the problem is, and this is where our sort of next one of the next technology problems is that your computer can't cope with that speed. It doesn't know
Mhm.
what to do with that, and that's sort of not really the topic for this conversation, perhaps, but technology wise, we need to learn how to send the data at that speed and accept it. So they can sort of do experimental measurements, but they can't do that. So there's lots of really exciting stuff just from that part. But then we get all this data and say, well, what do we do with the data? What are we observing? What are some of the questions that we're trying to answer here in astronomy? And some of the big hot topics now. So the James Webb Space Telescope, as you mentioned, that's just launched not long ago. They've had I think it was the end of last year, but they've had their first images was a few weeks ago, and they were amazing. They were looking back to the beginning of the universe because, of course, when you get images of these really faint, distant galaxies, you're looking back in time. And in this case, we're looking back sort of 12 billion years or more
Mhm.
to some of the earliest galaxies, and that's really really cool. Um, and the biggest challenge that we have, and then we're also looking at planets around other stars, and they've started to directly see them. In the past, we sort of had to infer their presence. Back in my research career, we had to kind of not guess. We sort of had pretty good indications that there were planets there, but we had to infer them based on other measurements. We didn't sort of have a direct here is a picture of a planet kind of observation. But the big challenge now is that we are swamped in data. We have so much data. I mean, these data rates that we're talking about, we will need to be able to process them and reduce them into something more sort of user
Manageable.
friendly or researcher friendly, manageable. But then if you want to actually do the science and the research around them, there's not enough researchers in the world outside of astronomy, let alone in astronomy, to analyze all this data. And that's where stuff like machine learning and AI is going to be incredibly critical for this in this field. In astronomy generally, we can't even imagine what's out there unless we have this kind of this because we just don't know. We don't know when you have 100. There are 200 billion stars just in our galaxy, 200 billion galaxies out there in the universe, give or take some in each direction. How do you analyze that? If you have all of the data on even some small number of those things, how do you analyze that data and get meaningful results out of it? So we need to be and we have started investing more heavily in machine learning, in data science and AI. In fact, just today I spoke to. We've just hired someone to do some
Well,
machine
congrats.
learning work.
They're tough to find
So
out here.
yeah, she just started today. So yeah, no, we're very excited about that. There's a lot of cool work that she can do. But this is the thing where we're really now at a point where when I did my PhD some number of years ago, uh, and I had tapes. I didn't even have hard disk really to store. I had tapes to move data around. Um, DAT tapes and those sorts of things. And I had to eyeball everything. There was no automated pipeline. There was no good way. I had to I looked at some ridiculous number of observations, 55,000 observations or something crazy like
Yeah,
that.
yeah.
Um, and but if we'd had some of the compute power and the data science tools that we do now,
Mhm.
that would have been a lot easier, and I could have found um,
Could have found
the
those stars a little
observations.
earlier, right?
Could have found them earlier, but also just the stuff because what we're really interested in, I think, is some of the outliers. So you know, to be able to filter out the stuff that you feel like you understand to some degree. And then you can look at like the group properties of all of that. Say, like, here are all the galaxies which are kind of, yes, these roughly fit into our understanding, but then here's the subset over here that are somehow different,
Different.
somehow an anomaly. And machine learning is really fantastic at just picking up that. So you've got some model, and you say this doesn't match the model. What is it? And then you get your researchers, rather than having everyone focusing on all the data, you have the researchers focusing on, hey, the weird stuff. What's this? What's this weird thing that doesn't fit our current understanding? And that's where I think we'll have a lot of progress in science. And then the amount of data that we'll have, we'll still need machine learning just to look at some of that too.
So how do
Sorry.
Yeah. So how do you actually do that? So how do you explain kind of AI and ML to the practitioners in your space? We talk about Eli 5, my CEO, but really for you, it's going to be like Eli 5, a government minister, or Eli 5, uh, my dean of sciences, or something of that nature. So how do you go about explaining machine learning in the astronomy space? And we'd
Uh,
love to hear what you do in terms of anybody out there. Please follow us on LinkedIn, YouTube, and ultimately anywhere you're getting your podcast. We'd love to hear your feedback as well. So please go ahead. So,
Yeah, yeah. I'm in. We're really interested in different industries and how you solve some of these problems. So yeah, I'm definitely keen to hear the listeners' viewpoints. But yeah, from our point of view, I guess, I mean, machine learning to sell to a government agency or a funding body like that, unless you're doing the actual machine learning research to develop new techniques and that kind of stuff, it's a bit of a hard sell. So what we normally would do is we start out with our big picture. We have our fundamental questions that we're trying to solve. How did the universe form? What is how old is the universe? What are we alone in the universe? How do planets and stars form? And all of these really cool questions. And we sell that, and then we bring in machine learning as these absolutely essential tools that we need to adapt and develop in order to answer these questions. So sort of, I guess, flip it on its head and say, AI is something that is absolutely essential, and in some cases even to just, as we were talking about before, to process the data. But it's absolutely essential if you want to understand and answer some of these questions. And astronomy researchers across Australia, but around the world now too, typically have sort of decadal forward looks, and that's where they ask. So these are the questions and the facilities and the things that we're starting to think about, and we want to answer these questions, and so therefore that's how governments decide how to invest money and things.
mhm.
And so in Australia, that's called the decadal plan. For astronomy, we're just past halfway. We're actually about to start to do a new one. It runs on sort of, I think it goes until 2025 in Australia. The US works on a 2020 to 2030 kind of
Mhm.
window. But that's where we need to start building in, say, the tools. And we started to use the language of machine learning and to start saying, yeah, these are the tools, and the deep learning as well, and some of these other things, just to sow the groundwork and make sure that when the funding agencies and the Academy of Science and all of these people see this, say, oh yes, this is something we've known about, this is expected. We don't spring a surprise on them and say, give us millions of dollars to do this machine learning business.
Absolutely.
They're sort of aware. So they're sort of,
N-
it's a well considered path
Yeah. So no
to get there.
surprises for the folks in your when you're trying to explain it.
Yeah, exactly, exactly. I mean, because no one wants to be sprung. Oh, by the way, we need $20 million or whatever it might be to do this work that we have never told you about before. so,
So
so
that
that's why
actually brings
it
us
always.
Yeah, so that actually brings us to kind of our segment we call kind of compare and contrast. And you kind of alluded to it a little bit earlier, kind of how you were starting out your career. But how has AI and ML really uh, compare and contrast with even things how we were doing things 10 years ago? What are you able to do now that you weren't able to do that?
Um, the big things at the moment is probably 10 to 15 years ago, we were just starting to realize, maybe a bit more, maybe 20 years ago, astronomy is quite ahead of the curve in many aspects in terms of statistics, which data science is heavily built on statistical
Mhm.
models.
We
Um,
all called it
and so
stats
20
back then.
exactly right, exactly right. So astronomers have always been interested in the group properties of things, because that's how you really get a good understanding. If you can sort of say, well, we have this model and it matches, and it sort of produces this theoretical output, and then you compare your observational output with that and say, ah, right, yes, it is good, or it's no good, or it's different in this way, or whatever. And so we've always tried to do, we've particularly looking at things like Monte Carlo simulations and those kind of things. That's always been a factor in astronomy, but we didn't have the sophistication that we're really beginning to need. So that there are a lot of people who are doing just very simple statistics across large samples of data, because that's what the tools available were. Nowadays, we can actually, using some of these machine learning models and various algorithms and things, you can really start to tease out um, how the theoretical our theoretical understanding matches or doesn't match on this very large scale. So we're talking, I think some of the first. So I'm part of the Australian Astronomical Optics group here at Macquarie University, but we used to run the telescope up in Siding Spring Observatory, and one of the first very large surveys of galaxies was called the 2 Degree Field Galaxy Redshift Survey. And basically, what they were trying to do was work out, um, they looked at 250,000 galaxies. They got all sorts of chemical information and their distances and where they were. Sort of, they tried to understand where they were in the universe, and
Mhm.
some of this stuff where, yeah, you understand at you know 500 million or a billion years ago what were the conditions in the universe, and that kind of stuff. And all sorts of really fascinating stuff came out of it. But and since then, we've evolved, and now we're looking at, from 250,000 galaxies, we're looking at millions of galaxies, and then into the future, we'll be looking at tens of millions. And once again, at that level, you can't have some poor student somewhere looking at 10 million galaxies. That's just
That's a
cool.
lot of galaxies to
So
look at.
exactly. And then the same goes for stars. So right now they're just finishing off a really important survey of stars within our own galaxy, within the Milky Way, and they're looking at the chemical fingerprints of all of those stars and trying to understand, the stars move around through galaxies, and they try to understand um, where all of those stars form. So did our sun form where it is now? Probably not. It's been moving around. They drift around a lot.
Yeah.
What other stars are similar enough to our sun that they probably all formed from the same cloud of gas? And
Mm.
then we do, so that's but we're looking. They've got 600,000 stars at the moment. They're aiming to get to about 1 million. And yeah, so machine learning is really coming to the
Yeah, you're not
fore
doing
there
that
to
as an
understand.
individual at that point.
Yeah, that's right. And we're looking at, we're talking about multi-parameter space here as well. So not just sort of, when you can no longer just say, oh, well, we'll plot temperature versus, the amount of helium or whatever, or iron or something like that. You've really got to look at a much more holistic view. And when you've got 40 different parameters, you can't really do that manually. That has to be done in some automated way, and you really need to
Mhm.
bring in um, some proper sort of statistical tools, and your machine learning is a really good example of that. And they're coming up with some really fascinating ideas and fascinating outcomes.
Yeah, interesting. So I guess in our next summit, we typically talk how do we make money, save money, improve the customer experience, and but I'm really interested in uh, for as astronomer, what what are we able to do? What's the value of what we're getting right now? Because you kind of started to talk about some of that. It's like how do we, you know,
Mm,
how did life start in our
yeah,
uh, in our universe? So, what are some of those things, those questions that AI and ML is helping you answer?
yeah. So I guess we start to get, astronomy has a lot of overlap with philosophy in a way. It's sort of,
Mhm.
what is our place in the universe? How do we fit? into the universe in some way. So obviously, as an individual, you might have your own views on that, but more astronomy is more interested in the Earth, how the Earth fits, and how life on Earth might fit, and so they're the really fundamental questions. So yeah, I mentioned before, is there life out there in the universe? Is it just on Earth? I mean, I think statistically, if you just looked at, I said 200 billion galaxies, 200 billion stars in each galaxy, give or take some, those numbers suggest it's statistically really unlikely that we're the only planet with life. We know that basically every star on average has at least one planet. So think of that as well. Um, and so the questions that we're really keen on are, is there life in the universe? How did life even start? How does life start on Earth or on other planets? How do the stars form? How do they live and die? And that's just say, at the stellar level. Then you go out to sort of the galaxy level. Well, why do we have galaxies, and why is it just not stars everywhere throughout the universe? Why are they sort of clumped? Because not only do you have galaxies, but you tend to have groups of galaxies and then spaces in between them where there's nothing much at all. And then, so how do you get those clusters and groups of galaxies? And so, we have some reasonably good ideas about this, but there's still a lot of outstanding questions. The cosmology, which is the sort of the big picture study of how did the universe form, and how did the early galaxies form, and we get back to some, not just astronomy but some heavy duty physics, where we say, well, you know how did all of the elements form? The Big Bang happened 13.2 billion years ago, plus or minus some number, um, and it created, from the Big Bang, after some period of time when we started getting not just energy and light, but electrons and neutrons and protons, we had hydrogen and helium and a little bit of lithium, and that was it. And so since then, we've generated all of the other elements in the periodic table. I mean, we're now up to well, stable elements, there's 92,
Yeah.
but we're up to 118 or something like
Uh,
that. The last
See how
one's
many
mainly
neutrons we
thought
can
to be
pump into
light.
something.
Exactly. Yeah, exactly. But yeah, so some of those questions, that's pretty fundamental building blocks. Understanding, you know, not just from the chemistry point of view, but the actual how do these elements form? How did we get to this position where we have just the right ratio of all of the elements and isotopes of elements and all of these things, so that we have life? And could that then go somewhere else? Because of course, in our galaxy, it might be not different. The physical processes are the same, but the ratio of things might be slightly different. So we're very interested in looking at all these other galaxies to understand their chemical makeup, and the stars. So we can look at stars and other galaxies as well, more like directly. So the nearby galaxies, you can actually, particularly with the James Webb Telescope that we talked about earlier, you can look at a star and get quite a detailed view of its chemical makeup, and things going on around it in its environment using the James Webb Space Telescope. I mean, they're quite focused on smaller regions, so the machine learning will still be important, particularly as I talked about with the models and the theories and everything. The ground-based stuff in the near future, where we're going to be doing these surveys, huge amounts of objects and stars, galaxies, whatever, and the processing needs are enormous.
Yeah, and I
Um,
think I
and
can
we're
imagine
quite
a
confident.
yeah, I can imagine a lot of deep learning. So we just had a conversation with Sheena Nassim, who's on my team here at Data IQ, where we talked about computer vision and neural networks and being able to and effectively go after a lot of that information. And I got to imagine you're going to be doing a lot of that stuff as part of a lot of what you're doing right now.
Yeah, that's right, and we're starting to see collaborations between astronomers and computer scientists, in that space to work on those sort of, neural networks is something that have been around in astronomy, been used for probably the last 20 years. You could probably go back further, but computing power was limited.
Little
I remember
limited
when
at
I was
that
a
point.
student. Yeah, I mean, I remember when I was a student, in the 90s, a PhD student in the 90s, we had at Sydney University, we had a Cray computer down the corridor, and it was all that was, you could get time on that and do sort of big heavy duty number crunching, and I'm pretty sure that we started to see the neural network kind of work being done there then. But the Cray of 25 plus years ago is nothing compared to the Cray of now, or other systems. I mean, I think yeah, we've. I'm hoping that we'll also see some new techniques developed to solve some of these problems too, because the scales, the data volumes,
Yeah,
some of the modern
tremendous. So you're
techniques
talking about a
are not
terabyte and yeah.
yeah, they're not efficient. Some of the algorithms that are currently around, they're not efficient at that scale. This is the thing. We need scalable algorithms, something that it might work fine if you've got a few gigabytes a day or a terabyte or two a day. But as soon as you get to 30, 40, 100 terabytes a day, um, you really start to
Yeah, you got an
struggle.
interesting set of problems. I'm sure a lot of people would be interesting to get their hands on some of that size of that data. So
Yeah.
we'd love to hear what you guys think in terms of what's going on in astronomy. What are your interests at this? So please follow us on LinkedIn. Drop us a comment here on the Proof of Concept podcast. Obviously, YouTube and anywhere you get your podcasts. So to wrap us up, Simon, kind of put on your prognosticator's cap. Tell me what's in the future, because you kind of alluded, we have the square meter array, we've got the, you know, what will come after the James Webb. It seems like there's so much potential, data, compute, all of the, solving the mystery of life, universe, and everything. And the answer is 42. It always is.
Totally is. We just need to know the question.
Exactly. So what are your predictions for what we'll be doing with astronomy and AI and ML?
Um, well, absolutely. I mean, I think the square kilometer array, and I just give a very brief overview. That's we're talking around about 3,500 radio dipoles. They're a particular kind of radio telescope in Western Australia, and about a similar number of actual dishes in South Africa and Southern Africa. And just, I mean, that's probably around 10 years away or thereabouts. Um, so I think we'll really be needing a lot of machine learning just to do some of that processing, because one of the challenges with those sorts of facilities is that we can't move the data fast enough and process it fast enough. So some of it will have to be done at the sort of the observatory site. It's outside of, it's well outside, it's 800 kilometers outside of Perth for the sort of the main set of dishes. So we'll need to have a combination of some kind of relatively simple but powerful processing on site, and then move the data down to supercomputing facilities, and then do the processing in Perth or in Cape Town, I think is the other site for South Africa. And so you know, I think what we are going to start needing is sort of machine learning on a chip. Where you basically have things done. You don't have you can't have a lot of heat, you can't have a lot of radiation and that kind of stuff. You want to keep it as minimal as possible, so you don't have interference with the actual observations. But you need to be able to do that. So you need to sort of use it as a first pass filter to get rid of stuff that is not real signal. It might be systematic uh, interference from the telescope or from something else, some other sort of background. We call it background noise or bias noise or that kind of thing. So I think there's that, but then just doing the analysis of this huge amount of data, I think that's where we're at there. And then coming online, we know about the James Webb Space Telescope, but there are a couple of other space telescopes in the works that will be much more what we call the survey telescope, and they will be taking these large amounts of data with a large field of view, and then doing this kind of what we call survey science. And that's really machine learning. Without machine learning and good AI techniques, there we won't be able to analyze the data properly at all. We'll be able to sort of process it, but analyzing it, we just won't be able to do that. So we're looking there, and then the Vera Rubin Observatory, which, as I mentioned, comes online roughly at the end of next year. There's always technical challenges, so that it could slip a bit, but that's sort of the ballpark. Um, that's going to be observing the whole southern sky in 6 different colors across the spectrum every 3 nights. So that's where we're getting, yeah, that sort of 30 to 50 terabytes per night. And then over the course of that's a 10-year survey in the first instance. Over the course of that 10 years, we'll end up with around about half an exabyte now. We're moving
You
into the
don't want your
exabyte
storage bill on that one.
regime. Yeah, and that's where we need new technologies to do the storage properly. I mean, you can host an exabyte of data, but yeah, the storage costs just to keep it cool and all of those things. But yeah, so that's that. You know, there's a big effort already online, ongoing to analyze that data, and we're involved a little bit in that work at the sort of the back end rather than some of the analysis at this stage. But the analysis of these data, um, you just can't do it without like proper machine learning tools. And that's where, yeah, because in those the Rubin Observatory data we're talking about is a 3.2 gigapixel camera that takes these observations. That's how it can do the whole southern sky at very high resolution so quickly. Three uh, 3 nights might seem a lot to take a picture of the whole sky. It's like, oh, I can get my iPhone out and take it, but it's the definition and the high resolution that we get, which means that we can do all this fine structure and interesting stuff. But that will, I think, we're looking at from that facility, we're looking at around about 1 million transient events per night, and a transient event could be something going bang, so a supernova, could be a gravitational wave event. So they're really cool, exotic things, but it also could just be, you know, asteroids and minor planets in our solar system moving across the sky, or comets, or that kind of stuff. And that's really important to understand as well. Our local, we've been
Yeah.
talking a lot about, the distance and everything, but local is super important to understand because we want to know
What's
asteroids that
coming
might
at
come
the
hit the
what's coming at the Earth?
Exactly right. So that kind of stuff. So that needs fast processing, and yeah, once again, you're looking at sort of AI and machine learning to alert, to look out and say, here is the thing. It's moving in this way over the course of the last few nights or few years. It looks we've got this trajectory. We can work out where it's going, and so you can set up an alert system. Say, oh, here is an object that is a threat or might be a threat, and then you get more data, and it's usually not. But still, these are the
Well,
important things
I
we need to.
yeah, and if I was to kind of put my own predictions on this, is someone who started out, basically when I was getting into computers, the SETI at Home program really kind of opened my eyes up to what was the potential impossible. And to be fair, the amount of data that's out there in the astronomy space and just stuff that we don't know about. I always come back to the question that says, are we alone in the universe or is there someone else there? And the answer to that question is fantastic if it's both, either one of them. So,
Absolutely.
Simon, I look forward to keep looking up, and I hope you guys are uh, keeping on it as well. Please follow us on LinkedIn, on YouTube. We'd love to hear your comments. Please download us anywhere you get your podcasts. Whether that's Spotify, Apple, etc. Simon, this has been such a pleasure for you to come into the Proof of Concept podcast. I want to thank you so much. Um, Everyone, take care. Thanks so much for listening to the Proof of Concept podcast. Have a great day. Bye bye.
Thanks, everyone. Thanks,